I'm gonna start. Okay. Welcome everybody to spring 2026 semester of Sensory Motor AI Journal Club. Yeah, it is my great pleasure to introduce Luke to you guys. He's gonna tell us about their continuous thought machine, and also I'm very excited to hear about his thought process and the engineering process that went into this discovery. So, Luke, why don't you first maybe like start by introducing yourself to us and telling us a little bit about your background, your interests and your career development and so on, like where are you coming from and like what are you doing right now? And then we can talk about your thought process and the engineering process.
Sure. Thank you so much, Hadi. So my name's Luke. I'm a South African. I spent the last 8 years before moving to Japan in Edinburgh, Scotland, where I was doing my PhD with Professor Amos Storkey. And I feel as though I tried my best to take an unusual route as much as possible. I wasn't particularly keen to chase the paper writing, I guess, method of doing a PhD, where you jump from one project to another and write papers, and then suddenly after 3 to however many years, in the UK it's supposed to be 3, but nobody finishes at 3. Eventually, you end up with something to show, and you submit that, and then it's the next part of your life. I felt as though during my PhD time, I would spend this exploring as much as possible. Now, I like to recommend this to people, but this is not not necessarily true for everybody. And I had the fortunate circumstances where I had already published several papers before I came and did my PhD. So it looked good on my CV already. So it made life a bit easier for me to do this. So as much as I like to say, do a PhD and don't publish any papers, easier said than done and less relevant to everybody. But that being said, I think my experience through my PhD was incredibly enriching for me. The title of my PhD was learning learning representations when proxy objectives fail. And what that really means is how do you get a neural network to do what you want it to do as opposed to what it wants to do? The primary example I like to use here is if I want to train a classifier between cats and dogs, and I set out to collect data for cats and dogs, I will go take photos of cats and dogs. Then I come back and I train my classifier, and I realize actually, no, I have a classifier for green versus gray because dogs are outside on the grass and cats are inside on the couch. And this desire, if you wish, this tendency of neural networks to fit to the easy parts of data. It's a greedy optimization algorithm. This is obvious, but how do you overcome this? And something I learned through this journey was you overcome this by being extremely specific for each problem that you face. And everything that I try to do this on, I had to have a bit of a custom bespoke solution. I started realizing more and more that that's pretty much what we do as neural network people who work in neural networks and design architectures, if that's what you like to do. It's what I like to do. Yeah. So after I did my PhD, I spent a few months in a sort of interim period working for a company called Altered, which does audio synthesis. That was where I was speech synthesis. And that's where I got immediate hands-on experience with working with transformers and realized how cool the technology was as it was sort of gaining traction. After that, I worked for Huawei in Edinburgh for just under 2 years. And I then came here to Tokyo to work at Sakana AI. And I absolutely love my job. I feel as though I'm in a privileged position where I think I have my dream job, and I get to do research that I love. I get to work with very smart people, and I get to essentially try guide the state of the research and make things that people pay attention to. It's a really nice position to be in where you publish some work, and inevitably, because the company is a bit famous, people will look at it and read it, and that's lovely, you know. and I feel a great responsibility to do as well as possible on that. Um, yeah, that was a bit
That, that,
about
that,
me.
that- that's very exciting. I mean, before letting you continue, can you expand a little bit on, what you described sounds a lot like just what academia should be like. You have freedom to just pursue ideas because they're interesting and you're following your curiosity and then you end up discovering something new. Is that really can you elaborate a little more? Is that the culture currently at Sakana? And do you think that's a fair description of what's happening?
It's a weird world we live in when in times like now that there are research labs that can sort of allow for these sort of approaches to occur. It's weird that a company that is for profit has maybe a bit more freedom than some research institutions might. I find that quite strange. And to answer that question, I think largely yes. Um, Cleon Jones, our CTO, is extremely passionate about having researchers do what they want to do because this is how we end up with good creative solutions. Um, Again, I think, a bit of a situation where it's a bit of a unique company in that sense that we've got one of the founders who cares so much about this. We have good investments and good financial backing and just just the right set of circumstances. I'm not sure if this is true for many of the research labs out there, but I do think that the line between academia and I guess industry lab is a little bit blurry at the moment. That's a kind of I know with my colleagues there's a huge range of what people care about, and caring about wanting your work to be useful and wanting it to be used as a product is also something really people care about.
Mhm.
And I do have one or two projects that I care very deeply that they become products, so I drive for that too. So it's quite personal. And our particular group at Sakana, we like to intentionally go down unusual directions and seek the type of research that others won't do unless we do. So it's a bit of an ethos in our sort of subgroup, but there's a sense of you can structure this the way that you wish.
Thanks. Yeah, that kind of paints a very interesting picture that, you'd wish that there's a lot more of that going on around the world, especially in academia, but yeah, let's not dwell too much on that. I think that's the really right policy to get innovation and encourage exploration. But it seems like at least what I'm perceiving here in the Bay Area is that everybody is just in the exploitation mode, the vast majority, let's say. And I think this should change very soon. That's my personal take. But anyway, yeah, don't want to derail too much in that direction.
Yeah, no, I hear what you're saying, and I think the explore versus exploit perspective is a hugely valuable one. It's something that Cleon and I have spoken about many times,
Mhm.
and I change my mind about it from time to
Mhm.
time. Uh, Currently, right now, I think essentially because of Claude Code coming out and really making such a splash, it's put me on the other side of the seesaw, which is to say, actually, there's a lot more exploitation that we can do with this technology. Um, but at the same time, when you try use Claude Code and actually give it a sense of what you're experiencing, in a visual way, I find that extremely tedious and very, very far behind using LLM tools and agential tools to, try do a visual task, try do a task where you're observing behavior and trying to actually get the model to understand that it's a pain. If things can be very neat and in tokens and in language, it's wonderful, and I think it's the right technology for the task. But beyond that, and I think this is a sensory motor journal club, and I think from a sensory perspective, I think we're still quite lacking.
Mhm.
It's my opinion that language itself already is a form of intelligence.
Mhm.
And I think bootstrapping off of that is what we've done, and I think rightfully so. Yeah.
Thanks. Yeah, I mean, I don't know if we were not planning to talk about this, but since you mentioned cloud code, this is something that I've been grappling with it myself. So I'm curious to know your personal opinion. Since the capabilities of these models are really, really, there's no slowdown in sight, in my opinion, and they're getting better and better. And it seems like maybe in a year we're not gonna even have researchers. We're gonna just have people who are working managing these agents. That's one way to like maybe like exaggerate a little bit. So I wonder, have you thought about this and have you prepared for it? Are you said that you're not using these agents as much as maybe you would like. So can you tell us a little bit more about like how this has impacted your own workflow and how do you prepare for this massive impact if it's coming our way?
Yeah, that's a great question. I've thought about this a lot, so I've got a lot of opinions. I'll try my best to express them as succinctly as possible.
Okay.
First of all, I think maybe every 6 months now, I realize that my ability to predict the future is getting worse and worse, and I think that that's because of a bit of an acceleration that's going on right now. Computer science is essentially, in if you want to phrase it in one way that you can phrase computer science is the science of bootstrapping. It's defined by being able to build things that can build things that can build things, and this is what we're experiencing now. I think AI is essentially just what computer science inevitably was always going to become, and I think that that's really fantastic. And I think having this perspective of where AI on one side and where humans on the other side is uh, certainly true, but maybe not necessarily the most helpful perspective to have. I do use Claude Code extensively. I think just over a month ago, I switched from pretty much writing all my code to writing almost none of it. And that, I think in the last month, I've achieved more than I probably would have for the rest of the year if I hadn't. I'm quite shocked by this, and it's fantastic. But finding those problems that still remain relevant, that becomes the core skill set as a researcher, is defining what the problem is and seeking it out. And this is where we turn to, how do you define your research agenda? And I think there's a lot of agreement as to some of the things that intelligence is doing on the basic level. And we'll talk more about this later in my talk because I have a slide expanding on it. But the point here is that there are things that we know intelligence does. It predicts, it makes observations. There's a feedback mechanism in intelligence that keeps, in brains, in biological brains, that keeps things in check, if you wish. And this self-recurrent mechanism is something that we know exists in biology. And the big question mark, and we took some steps in the CDM to try build some of these out, but the big question mark is how do you engineer it? And you can't just one shot this with an LLM. You can't just build this out in one way. And the reason for it is all of the training data is wrong. We haven't done it yet. We haven't got something that mimics a brain in a way that is convincing to me yet. We've got an incredible kind of intelligence that is a language model, and it will always be so, but it is a different kind of intelligence than what brains are implementing, in my opinion. And I think that the way that people think about building neural networks is in the training data, strongly in the training data. Mm-hmm. And I've noticed a lot of the time when I try to solve tasks with Claude Code, for instance, I bump up against what I can see other people have done, and I bump up against the ways that people have thought about the problem before me. Mm-hmm. And I guess the way that I like to approach this is to think how do I think we need to do things differently? What is wrong with the status quo and the norm, and how can we think about this differently? And then I find that these language models have holes, and I become more relevant.
I strongly agree with that. This actually validates my own personal experience in different projects. Whenever I want to just fit a model that has been repeated in the training set, like let's say I have this new optimizer, I'm going to try it on a Llama architecture. I don't have to know what Llama is. I just say like, Cloud, please just code up a Llama architecture for me. That's perfectly like in one shot, it gets it right. But then when it comes to more like brain inspired architectures where you have these like iterative inference algorithms with spiking networks, these are the things that have not been explored enough. They're still niche. They're still tail distribution, and it makes me feel relevant. So that was it. That was
yeah. Yeah, I think what LLMs are asking us to do as researchers
Yeah.
like from the philosophical point of view, is to ask the right questions.
Hmm.
I think intelligent beings ask intelligent questions, and I think it's a really good thing for humanity what is happening right now, because what it is it's forcing us to grow as a species, forcing us to become, less complacent about how we solve problems, which is, kind of the definition of life in a sense, just continuously clawing your way up and solving the problems in front of you. And currently, right now, in terms of intelligence, the species is being asked to solve a specific problem, which is how do I be intelligent in an age where intelligence costs a click?
Perfect. In that uplifting note, maybe, okay, let's just go to the next stage of this presentation. Okay, the next stage is, of course, there's two things that we wanted to discuss. One is your own thinking and ideation and engineering process. Do you have slides for that, or is this something that we can continue talking about, or do you think we should switch to the technical presentation? It's up to you. What do you what should we do next?
Right. Okay. So I'm going to talk about this a bit, and then we'll come back to later on in the presentation because I
Mhm.
will demonstrate what I'm talking about.
Okay.
But very quickly, I want to, pitch to everyone here that in 2026, there is a better way of understanding your research. I
Mhm.
really do believe this. And by that, I simply mean tooling. It is quite simple and quite easy right now to go into your repository that you are, basing your current project about and build out tool systems. And I'll explain what I mean by that. Tool systems that can let you understand your experiments and your results at a level that is far deeper than what we've ever had access to before. And I'm surprised at how few people do this. And the simple example, the thing that I currently do, and this might change. Okay, so what I used to do, and when researching the CTM, I had this vision in my head that I wanted to see neurons that were active. Like as simple as that. I want to see dynamic neurons in a recurrent system that are not just flat lines, that aren't just going towards some fixed point. How do I get this? Okay, a lot of engineering, and we got there. How do I know that I get there? And this was visual, of course. And I had to build out visualization pipelines that I could inspect the neurons, and I'll show later some UMAP representations of those neurons and see how they're active. If I were to just measure the performance on a classification objective, whether it's solving the mazes that we solved or ImageNet, the numbers are within sort of standard deviations of each other. They're identical. On one side, I've got a system that looks dead in a sense. The neurons are not active, they're just attracted to some point. On the other hand, I have neurons that are highly active and diverse and actually doing the thing and behaving in the way that I think is how we should go. But with statistics and supposedly sufficient statistics about the task, I can't tell this. So I had to do things visually. And I built GIFs, I leaned heavily on matplotlib and just built out all of these things that as my experiments are going, every few thousand iterations, it would dump a bunch of images and GIFs into my experiment folder, and I would have a look at them and see, okay, after a few hours of training, this is not working. I kill that job and do something else way before I got any sort of results. And I find that this is not something that people do enough. And you might think, oh, but for my problem, I can't be so visual. But I would beg to differ. I've worked on all sorts of domains that haven't been image based, and you can always find a way of visualizing and gaining a more qualitative perspective of your work. And this is something that I push, and it's a bit alien to a lot of people that we don't do this. So I used to do it like that. Now, because of like good coding agent tools, now what I do is I basically go into my repo. I do this, I upgrade this process like once every few weeks. All right. I'll go into my repo, but from a one-shot perspective, I will then ask my LLM of whatever you choose to please build a web app, just an HTML file, right? That when you're logging, you've got your eval log step, you've computed your eval losses and you dumping them into weights and biases or whatever you use. Also make an HTML, standalone HTML document with nested JavaScript, CSS, all the works, such that you can literally just open it and then interact with what's going on with your model. And I'll show you examples of where I'm at with that later on in the presentation. But that is trivial. And because language models are so good at anything web development related, it's basically a one-shot process and it's easy. And the sort of things that you can do, the number of problems that I've solved and bugs that I found that I would never have found before by just doing this and interacting with what I get out of this process, like there would be no chance I would be able to do any of the research that I do without this. And I feel quite strongly that people should do more of this because it's easy and it's nearly free.
Thanks for the explanation, Luke. This is very exciting. I'm actually very curious to see what you have concretely because when you were describing this, my thought was, okay, yeah, how is this different from just weights and biases, just like different panels with different metrics? But you mentioned HTML, and it seems like this is different. So I'm looking forward to seeing your explicit example. And I guess, do you have to have some theory or a hypothesis that guides which things to track, or maybe like this is something that you might mention? That's just a question that comes to mind. How do you choose what to visualize and what to track, apart from the loss or that gradient norm, like the normal things like that?
Yeah. So I work a lot with vision and we'll be focused on vision today. So vision is easy, but I think because this is a brain inspired um, set of talks that you're doing at the moment in the spring, and because CTM is brain inspired,
Mhm.
uh, my sort of philosophy with this is that thought and intelligent action takes time. When
Mhm.
you've got a time dimension to this, what you visualize becomes trivial. You visualize what the model does over time, and from different perspectives. I've worked in the time series domain in the past, and of course that you can visualize things like forecasts, and you can visualize the relationship between tuning a certain inference parameter real time versus seeing what the model's done. Of course, you wouldn't nest the model in this sense. You would rather just try different variants of this and be able to switch between them on the fly. But it really depends what you're trying to solve. If you're if you're able to sort of tweak certain parameters in your system and have a look at what the differences are, then I think you're onto something. Uh, it's personal depending on the project. I have sat down with a number of my colleagues and interns, for instance, and spoken this out with them. And we'd start at a slate where we don't know what we're visualizing, but it becomes extremely specific and very obvious when you start digging down into a single project. And it becomes easy when you just start asking the right questions about what it is you're solving. Like what do you need to see in order to get a feeling of success?
Mhm.
What is the way that my old PhD supervisor used to put it was, what is the killer app of your project? If you were to put it on the App Store and make millions, what would it look like? And try to build that. And I wish I could give you a solid, like, this is what you look for, but every time I've tried, it's been extremely specific to the project.
Yeah, but I think the philosophy here is very, I think, the important part, right? Because we have defaulted to this view that we collapse the entire behavior of the model to a single number, let's say performance, or a set of very low dimensional measures like performance is one, gradient norm, whatever that is. But then you're saying that no, that's a big part of doing research. You have to take time to think about what is the measures into the behavior and dynamics of this model that will reveal its inner working. And I guess the good news is that this is not the brain. You have full access. You can measure anything you want. You just have to take time to think
Exactly.
about it. Yeah, that makes sense.
Exactly. And you'll often find bugs in your implementation or an LLM's implementation when you do this. I continuously do. And this is actually one of the reasons why I don't worry too much about what the code looks like.
Mhm.
Um, I've been a software developer in my past life. I know how to write code. I don't have to worry too much about it because I know that if it's not working the way I want it to, it's not going to yield the behavior that I'm after.
Mhm.
So I like to tell people that I care about the behavior of models before I care about their numbers. And when the behavior is correct, that's when we'll start building the metrics around understanding what that behavior means downstream for objectives. And yeah, it's a bit counterintuitive to be behavior first or qualitative understanding first before actually caring about the numbers. But consistently find that I developed the metric framework to understand the performance of a model way later in building out the visualization framework.
Well, I think cognitive scientists would beg to differ. So because for them, it's behavior is everything. So
Yeah, yeah, of course. But I mean, I'm talking more about the sort of
yeah, yeah,
mainstream. Yeah,
mainstream
yeah. I
data.
mean, one example with these um, visualizations I can give you just off the bat is I was training the CTM on language modeling, where it was tasked with predicting several tokens ahead. By several, I mean up to like 50. And its CTM's got this internal thinking process to it. And you can then visualize at each step of its internal thinking what it thinks is next
Mhm.
in terms of the whole stream ahead, like the whole sentence coming. And what's fascinating, something you will not see in any of the metrics, is that even though the numbers stay similar, at some point in the training, there's a switch where it stops sort of averaging and then starts exploring different ideas. And this is just completely subtle and completely hidden from any of the metrics that you measure. We saw the same thing with the maze task, and I see it in almost all the tasks that I train on. There's a point in the learning where something changes and it looks different. And this tells me a bit about uh, how there's different stages of learning with neural networks, and we know this. This is not new, but there's a lot of good theory on this and a lot of good mathematics on it. But seeing it visually and qualitatively feels a bit real, more real to me because it's my problem and I can see it happening.
Reveals the phenomenon to be explained later.
Yeah, but I will get back to this later and I'll show you some examples. Hopefully that'll be exciting.
Yeah.
But yeah, perhaps we can dive into the CTM itself.
Perfect. Yeah, let's so I can give you permission to share and we'll go to stage.
Sure. I'm probably the goal here is that I'm going to be jumping between slides, a into my interactive website demonstration because it's much easier to show results in there, and probably I will draw some things out with my iPad and share them. So bear with me if there's some technical difficulties, folks. I'll do my best.
Sounds good.
All right, let's see if this works. All right, I can see that you can see that, but
We can see your screen, yes.
yeah, which one? Can you see
We see the slides.
All right, that's the wrong screen. Let me try the other one. Yes, that looks right. Okay.
Mhm.
But you should see the slide and the UMAP is playing now.
Yes, we can see that.
Alrighty. Okay, that's good. Then that's sharing my second screen. Great. So yeah, thanks for the chat. That was really fun. I think now obviously the time is to talk a bit more about the technical details of the continuous self machine.
Mhm.
I like to try to begin these slides with visuals, as you can see. And something that we didn't speak about a minute ago was how important I believe um, communication of your work is. And this is why I have pretty images. This is why I've got a UMAP playing on the left. These are neurons firing in the CTM as it's thinking about ImageNet, by the way. And then to the right, I have some crazy looking drawing. And this was my first attempt at building an architecture diagram for the CTM for people to understand. We put this as like, a pretty thing on the website. But in actuality, this was, me trying to do a better version of an architecture diagram. I put it here because I just like it. It looks nice. Alrighty. Okay, so I'll rush through this a bit because I think we've mostly spoken about this. But yep, I'm a research scientist at Sakana AI in Tokyo. Did my PhD at the University of Edinburgh. Primarily, I see myself as a builder, and as creative as possible would be nice. Some of my hot takes and research interests. Uh, I care about building a digital brain that's nature inspired. And I'm asking the questions: what does it take? I definitely haven't got there yet, but we're trying our best. I think that vision, not just visual data, but the vision the action of vision is still an untapped resource, and that I think we're going to see some great advances there in the future. I think that observation, prediction, action loops, as I like to call them, beget recurrent models. And I think the CTM was a bit of a preparation for this. And I think that time is an underestimated resource, and also that time is extremely difficult to work with. I have worked in time series modeling in the past, and it's one of those fields that silently goes unattended to by many people because it's really difficult, much more difficult than what one might expect. You know, I would very much appreciate if people interrupted me and asked questions during this presentation. So please feel free to, anybody and everybody. We will have a time for questions, but at the same time, I don't want to gloss over something where I think it's understandable because I've thought about it too many times, whereas it's going over your head. So please do interrupt me. I would appreciate that. And you would get many brownie points with me. All right. So overview of the bit of the technical side here. So we'll talk about continuous thought machines. Why even do this research? Go for an architectural deep dive. Talk about some of the intelligence principles, which is what I spoke a bit about earlier. Describe some of the tasks we solved in the first paper, and the losses themselves. Not something we speak about too much in the paper, but I think it's important to understand. How we evaluated things, very simple, and I think a nice discussion on some of the emergent observations. I mentioned how there's like a switch over in some of these tasks, and this would be an example of one of those. Then I think I want to talk a bit about active vision and what I'm trying to build for the version 2 of the CTM. And I'll show some tentative, qualitative results. And this will be when I demonstrate the sort of HTML-like process that I'm after. All right, so why? Like, why work on the CTM? There are brilliant minds all around the world trying to engineer parts or engineer ways that the brain works for very good reasons, for building better models, for understanding the brain, for healthcare, for a number of things. Why should we build the CTM? In actuality, I was unable to sleep one night some time ago. It was like almost 2 years ago, where I was thinking about how neural networks just don't do things the way that I like them to. They're not very much like brains, even though they're neural networks. Instead, brains are these complex dynamical systems. They're capable of continual learning, online adaptation. They're extremely robust. We've got mechanisms in the brain that we barely understand, that we can sort of talk about and feel out, but engineering those things just feels so far out of reach. Neural networks typically, I think not so much with language models and autoregression, but typically they are feed-forward data processors. And by that, I mean data comes in, something internal happens, and data comes out. Excuse me. And there's no real concept of time in these models. And this brings me on to the central tenet of the CTM research, which is thought takes time and reasoning is a process. What do I mean by that? If I were to freeze time right now and slice everybody's brains open and measure something about the neurons, I don't think, if we had the tech, I don't think I'd be able to decode your thoughts. Instead, I think that what a thought is, as a process, is something that exists over time. If I were to be able to record your brain for 10 minutes, perhaps then I might be able to decode your thoughts. But I don't think that snapshot of reality is nearly enough to understand what an intelligent being is doing. So I wanted to build this in, use time as a resource. If we make it the central thing that the model uses, what do we get? Just a very open question. And how can we engineer some sort of stable dynamical system where data processing is obviously necessary, but secondary to the notion of alive neurons, as I discussed earlier. And really, what I was after when building this or thinking about this was how do I make something with as little engineering overhead as possible that is still very good at working with GPUs, but that has a few sprinklings of properties that brains have. And what is that bias? So, yep, essentially asking the question of what new capabilities we can unlock with nature and brain inspiration. All right. I had to be very cheeky and cheesy with that slide. Okay, so this is the architecture diagram of the CTM, and we're going to dive into certain parts of this. Again, I tried to make this look a bit different from the norm just to catch attention, use colors. Uh, but we'll start from one and make our way through to 9 or 10, somewhere over there. And I'm going to try to decipher some of these things, and this is where I expect interruptions. Okay, so we'll start at number one. This is what we call the synapse model. It's very simple. It's just an MLP. In our case, it's like a UNet design. So there are several down steps and several up steps in order to yield what we call pre-activations. All right. So as inputs, you have this latent space. Z is the latent space that the neurons are occupying, if you wish. And the inputs to this layer is that. So this recurrence, the self-recurrence that is native to the CTM, and concatenated with the outputs of attention. And we'll have to loop back. There's no real good starting point on this diagram because it is a recurrent diagram. So I did say the outputs of attention, but then I have to describe that, and I'll describe it later.
Are these just real vectors of real numbers, Z and O?
Yes, very, very simple, just latent space. Yeah, just normal representations.
Okay.
Okay, so the output of this is what I like to call pre-activations. One thing that's worth spinning on its head here is when I when I think of a ReLU nowadays or any sort of activation function, as in neural network speak, I think that is in a large sense maybe misnamed. I think we know what they do and what their purpose is to turn a linear system into a nonlinear system. I don't think that they are nearly anything like an approximation of what actual neurons do. So this is why I call these outputs of this synapse model pre-activations. They're what go into the neurons, essentially. Right. Speaking of the neurons, what we have over here, well, let's discuss pre-activations a bit first. All right. So pre-activations are basically a ongoing rolling list of these outputs of the synapse model. So it's again a d-dimensional vector, and we just collect m of them. And m is what we call the memory length of the CTM, or the neuron level model memory length. And this is basically just a first in, first out queue. So if you imagine it like a matrix, on the right-hand side would be the latest one, and on the left-hand side would be the nth oldest one. When you get a new activation, you pop it on the end of on the top of the queue, and you drop the oldest one. It's just a first in, first out queue. All right. So why? And what is this? So essentially, each neuron, the neurons in the system, this is a time series, an m-dimensional time series. And this goes as input into the neuron models. And the idea here being that it captures a very long-term history of what the pre-activations into this neuron are doing. Turns out that doing this gives really good gradients and actually helps a lot with the learning, because in a very real sense, it's very recurrent with lots of skip connections. So there's n different connections down back in time. So it really helps with the gradient vanishing problems in a recurrent system. The other reason this is interesting is I asked, how do I complexify a neuron? How do I make it more like a real neuron? And I don't think that real neurons are taking time series in the brain, but this is a dimension over which we can complexify. And this was essentially preparing for that. Alrighty, so then we have neuron level models. We take a single one of those dimensions in the latent space of those D dimensions. And what we do is we say each one of those neurons has its own MLP. So it's a private model with its own weights, and this neuron takes in its m-dimensional time series and processes it forward into a single scalar number. The idea being here that this is intelligence implemented at the level of a neuron, more similar to what brains do. One could take a theoretical tack here and say, well, uh, infinitely wide neural network with a single layer is able to approximate, the universal approximation theorem, able to approximate anything. So maybe it could approximate what a neuron does. In this case, because it's got a time series in, maybe that helps. I'm not making any definitive claims that this is what a brain is doing, but definitely this is an important part of the CTM system. And I think it's something that people haven't done before, which is why we did it.
Can I ask a question about
Sure.
details? I want to
By all
understand
means.
the dimensionality. So the dth column of that matrix A, it was just a vector of dimensionality m. And then
Yes.
when you collapse it, the z is just a single number. So it's like a huge kind of reduction in dimensionality. It's just maps the entire
Yes.
vector to a single number.
Yes. Precisely that. So you have a matrix essentially that you're then collapsing to a vector along one of the dimensions, and that dimension is time.
And this number is still just a real number. There's no sense of, the activation functions in typical standard machine learning, they have to be positive, but you don't have that constraint here.
No, there are the typical activation functions in these MLPs and
Oh,
in the
in the
synapse model,
MLP,
like
yeah. Okay.
like a like I think we used either GLU or SILU. It's not really important which one, but yes, when I say MLP in both these cases, I do mean in the typical neural network sense that there is a activation function inside at the second layer.
Okay, makes sense.
Go ahead, Leonard.
So you're looking at a fixed like slice of time, right? It's when you start this off, do you pre-fill it with like zeros, or what does that look like?
That's a great question. Yes. What we do is we pre-fill it with a learnable space. So you could pre-fill it with zeros. It turns out it doesn't really matter that much. And you touch on what is, I think, in my opinion, one of the biggest pitfalls of the CTM system is exactly that. You've got to have this pre-fill space. At least the version one version of the CTM. And this pre-fill space essentially defines an algorithm that the model follows, which is what we found. So if you take that pre-fill space and you populate it in a data-driven way, so I get it somehow from your data, turns out that the CTM has less of a bias towards following a fixed algorithm versus actually doing something more data specific. Yeah. Does that answer your question?
Yeah.
All right. Okay. I'm going to move on then. All right. So now we've collapsed this m-dimensional vector to 1, and we get a small z, z1, 2, and t, and we collect these. Again, we're now building a time series, but this time series is not first in, first out, FIFO Q. This just grows. This grows up to t, where t is the current time step in the recurrence. We have this collection of vectors over time. And why do we do this? I'll go back to what I said earlier. Thought takes time and reasoning is a process. It's not the snapshot of neural activity that captures the thought, but the evolution thereof. And again, like I mentioned, good gradients. And the reason for why we captured this is actually an engineering one, which will be explained in a minute. All right, so next up we have synchronization. So synchronization is one of the core features of what makes the CTM work. All right, so what is synchronization? We take this growing time series of z-dimensional vectors, so this collection Z, big ZT, and we just measure the cross correlation, or the correlation between all of those neurons. This gives us a massive D by D matrix, that is the synchronization matrix. And it's basically just measuring how do these individual time series in pairs sync up? How do they correlate over time? And I'm going to dive into this in a minute to explain more about how synchronization works, because it's an important point, but I'll be switching over to draw things out for you in a minute. But why do this, first of all? So captures a sort of neuron level cross-firing idea. And what does that sound like? It sounds a lot like Hebbian learning. What fires together wires together. So the representation that the CTM has, that thing that then gets fed for downstream use, that is a synchronization representation. So in other words, the CTM's way that it takes actions in the world is conditioned on something that is synchronization bound. And it's as simple as that. But I think I'm going to switch over to I think I'm just going to switch over to the to my iPad for a minute and then draw out what synchronization is, because it's very difficult to do without that. So bear with me for a moment. All right, can you guys see what looks like a drawing board?
Yes.
Perfect. Okay, so I want to describe synchronization because this is a really important point. And I want to caveat this with synchronization is something we know brains do. Neurons synchronize when we take measurements of the brain. We're actually measuring populations of neurons because they're in sync in some way. And this is biologically inspired, and we certainly pitch the CTM as being biologically inspired. But ironically, designing that was not at all why I built synchronization. It was actually an engineering solution for a problem I was facing. And I want to describe this problem now because it's fascinating that a biologically plausible solution is the solution that solved this problem. All right. Before I do that, though, I want to remind you what we were exploring, or what I was trying to get here. I wanted a system with dynamics that were active, that could solve a task. Right? So neural dynamics, neurons that change over time and are free to do so, such that they can encode information over time. Okay, that was the goal. And the synchronization was an engineering solution that overcame something. And I'm going to try to explain what that is. All right, so imagine we have a neuron that's firing over time. We have a second neuron that fires maybe slightly differently over time. If we were to measure what the relationship of these two neurons were to each other at this point, so this is at some ZT, all right? Now, what we do is we say, well, this neuron is a bit positive and this neuron is quite negative. Maybe it's +5 and -2, and then we have some snapshot representation. So what we could do is we could take this representation, and this is at ZT, and that can tell us something about the system at this time, right? If I then roll forward a little bit further in time, and I take the snapshot over here, right, and I measure this, maybe t +3, I get a very negative number over here, so maybe -3 and -5. Now, the difference between these two states is quite substantial. In one setting, some of the neurons are high and some neurons are 0, some neurons are flat, and that traces out a certain geometry in latent space. Later on, very little has changed, but the geometry has changed dramatically. And if you try to just take this, and project it to maybe like logits or something with another layer, at the end of the day, it's really hard because you take one or two more time steps forward and your process, your Z space has changed dramatically if you're assuming dynamic neurons. So if you don't do this, what do you get? You end up with a system that looks something like this. Neurons will follow this sort of behavior. And you get these flat sort of dead neurons, I like to call them. They're not dead, they're encoding information as a population, sure. But they're this stable attractor in the neuron space that to me is just not what I was after. A little bit boring. So I asked, how do I then solve this? And the answer is obviously synchronization. That's what I'm getting to here. But why is it synchronization? Let's redraw this. One neuron that fires like this, another neuron that fires like this. So synchronization basically says, how do you line up over time, where time is this internal dimension? And what we do is we just measure the dot product over time. We get some numbers and we just sum over this dimension. And this gives us a scalar. This makes the system a lot more robust to small perturbations over time for, I think, obvious reasons. There's another part of the synchronization that is really interesting. And this extra part is we place a exponentially decaying weighting function in between these neurons. So this is just defined by a learnable exponential decay where we have a learnable sort of alpha parameter for every pair of neurons that we care about. And what does this mean? If I were to have an exponential decay that biased towards long-term slow changing signals, it would be flat. But I could also have a exponential decay that biased towards very short-term signals, and it would be very sharp, and something in between. And basically, when we train the CTM with these exponential decays inside there, we see a vast range of different decays. And this means that the internal structure that's organizing itself is essentially saying, for some neuron pairings, I'm going to care about very, very sharp, like now. As this representation changes, as it changes together, that's what I care about. But for others, I care about a much longer term periodic behavior if it's there. Turns out works really well and solves the engineering problem that we had, which is this snapshots end up like this. You could solve this many other ways. You could naively take these snapshots and then put this through like an accumulation type holding thing with a neural network. And you just have to make that neural network that maps to an accumulating representation quite large and quite powerful. Or you could take a convolution that takes a bigger section of time and do something similar to that. Turns out that synchronization is simple, cheap, and super effective at doing exactly what I wanted to do. All right.
So do you introduce these exponential decay parameters? There's probably like d times d minus 1/2 of them, right? And you introduce them as free parameters to learn, or how do you add them to the model?
Yes, free parameters to learn, but we getting to this in a minute. We don't take all d squared pairings or d times d minus 1/2 pairings. Like we don't take all of those. Mm-hmm. We subsample them because that's a huge amount. There's no point.
Okay.
Yeah. But we just set them as learnable parameters in the system. It's actually interesting. You mentioned this in the version 1 paper. We describe how we didn't really see changes in these. If anybody's read the paper, and we were kind of shocked by this. Turns out there was just a big bug in our code base where essentially we were taking absolute, and taking this absolute meant that as soon as the neurons themselves got into a negative space, they couldn't escape that because there was no gradient. Mm. And when we released this publicly and open sourced it, one of the first things that somebody picked up was, hey, this is broken. They fixed it. I retrained some things, and then exactly what we expected, diverse neurons doing all sorts of things, just fell out after this. Random stranger on the internet fixed it for us. I just love that story as an example of how powerful open source can be. All right, just going to continue with the presentation here. All right, actually, you can see that. Okay, so let's talk about what we do with the synchronization representation. We do action and we do prediction in the CTM v1. And action for me is the most exciting thing here, and this is what a lot of our results are on. As I mentioned earlier, I care about behavior, and action is a bit more tuned to that, I think. So you can see we have a S action and S out. So these are synchronization just at the beginning of training, and this is important to note. It's not during the whole training run. It's at the beginning of training. We sample a subset from this large synchronization matrix. And one subset goes to action and the other subset goes to outputs. And we have linear or nonlinear MLPs. Doesn't really make a big difference. These weight matrices that map portions of the synchronization matrix to either queries for attention or logits for prediction, or whatever else you want to do with them. We've tried many other tasks that we didn't publish, things like image reconstruction. You can do regression with these things. I'm doing all sorts of strange things with them at the moment. But why? As I said, the full synchronization matrix is huge. The notion of synchronization as a representation for me is quite exciting. And I like the idea of conditioning actions and predictions on something that is richly temporal, not just a snapshot in time, but can be trained or can learn what sort of periods and frequency or periods and changes over time that actually matter.
But I just wanted to add a comment, if you don't mind, about this synchronization as representation. There's this literature in fMRI neuroscience literature that they look at pairwise correlation matrices in an extended amount of time, and then it turns out you can decode phenotype, like a person's IQ score or something like that, from the pairwise correlation structure from fMRI. They call that functional fingerprinting. And it seems like what
so cool.
what you're showing here is kind of like the machine learning version of that. You're decoding all those things from pairwise interactions.
I did not know about that. I'd love to read that paper. You should please let me know what it is.
Yeah, I'll send it to you.
Thank you so much. Yeah, that sort of kind of speaks to something that we continuously see with CTM is that we build things from really like a hacking, or I'm a builder and a hacker far before I'm a scientist or a mathematician. I believe in science and I use it, but keep on figuring out that, there's something that we did with the CTM that is actually similar to biology. Some weird esoteric part that I didn't know about. And I love hearing about these things. It makes me very excited.
Nice.
All right. Yeah, so what I'm showing you here in this current image that's playing is a set of neurons in I think it's the ImageNet CTM. And these are the foreground one, the one that's sort of dark. That's as they're changing each time it's fixed. That is for an individual image. So it's one example, right? So why do I switch between them? It's just to show that there is diversity in the way that the neurons are firing for different images. So you can see quite often that there will be a neuron that has very little deviation from the mean. In the bottom right corner, there's an example. And I don't really know why this is the case. I don't really understand too deeply why some neurons decide to like encode what feels like algorithmic timing, and other neurons seem to encode more diverse features in the set. It's surprising to me. Yeah. So as I said, it's an engineering fix. And yeah, please go ahead.
One thing I thought about earlier that might be relevant here. Have you thought about looking at it like an interpreter? Like you have
No,
one
can you
part
explain?
that's like you have one part that's data, one part that's like bytecode, and then you interpret um, you run a program in memory. Like you store the
I
program
see where
as
you're going with
data,
that.
and part of it is just like the machinery of how it needs to work.
Yeah, I think that's a really good perspective. Um, I'd probably share that it's difficult. It's difficult to sort of latch onto one of these as being the perspective that one holds when researching this, because as I go and I tweak things and I spend my time doing my research, uh, I can get this behavior to appear more or disappear depending on how I set things up. Um, Hyperparameter sensitivity, not necessarily hyperparameter sensitivity, but architectural uh, sensitivity. So I mentioned earlier how the pre-activations, and I'm visualizing post-activations here, so after the neuron level models, but pre-activations follow a similar structure. If you were to start those instead of with a learnable or a zero space, start those from data, you get much less of this, and it becomes much more data specific. So yeah, that's interesting. Also, in this version 2 of the CTM, we have multiple stacked CTM layers. All right. So in this version, we have a single layer that does everything. It does the querying for attention, and it does the prediction. Shockingly, when you siphon those off, so you have one layer that's for attention and a different layer that's for prediction, the prediction layer looks much more algorithmic, like very little deviation between, and by prediction in this case, it's classification. Very little deviation, much more close to the mean. But the query layer, the one that's taking action, hugely diverse and very, very meaningful and rich with information.
Yeah,
I don't really, yeah, go ahead.
oh, could you elaborate a little bit on how you've scaled the CTM up since the original paper and added more layers, as you mentioned? I'm very curious how that fits with the
Yeah,
existing picture.
nice to meet you again, Henley.
Oh my gosh, you remember wow.
Yeah, um, I will elaborate a bit later on.
Yeah, no worries.
I can't share everything, of course, and but I
Oh,
will.
no,
I'll
yeah,
get
no
there.
worries.
Yeah. Okay. So let's talk a bit about the tasks and the losses for the CTM. Um, so we tested on a bunch of things, but I think for me the most exciting one was just navigating mazes. It's a toy problem, sure, but for me it was the what we like to call at Sakata the, or at least in my little team, the hello world problem. So when we solved this and we could see the behavior emerge for this, for me, it was a bit of a eureka moment. Like, yes, now I can see this type of behavioral sequential reasoning emerge. And this is why I love this task so much. Mazes are trivially easy for a machine to solve if and only if the maze is presented in the right format and the outputs are in the right format. The easiest way to solve a maze, one of my favorite papers in this space, is to take a maze and put it through a CNN, but the output is the same shape, also an image, and the targets are just zeros and ones. And one for is the path and zero for is not the path. And if you train this in the right way, you can then scale this up to arbitrarily big mazes because it implements like an A-star search down the maze. It's great. You can do this. Machines can solve this task. But if you limit this to a way that requires a sort of problem solving methodology like humans do, it becomes exceptionally difficult to solve. Right. So for our purposes, in order to inspect this as a problem that we want to see behavior on, what we did was we said the output is not an image. The output is a sequence of steps. It's just classes. All right. Those steps are left, right, up, down, and weight. And weight in this case is just padding. And I'll explain that in a minute. The inputs are an image, very importantly here, without a positional embedding. And the reason for this will become clear in a minute. Interestingly, if you add a positional embedding, it ignores it, but this is specifically without a positional embedding. The reason for this is intuitive. If I want to look at a maze in a certain place and then decide I'm going to move the path up and to the right, I need to look at that and imagine what that path looks like in order to lay the path down. So it begets a world model. It's this planning idea, sequential reasoning. So I'm going to try hit this home a bit. What this basically means is, what must the model do if I don't want to talk in a human sense, right? The model needs to build an attention query that maps to a certain path of the maze where it's currently thinking about. And then in order for it to look at the next part of the maze, it has to change that attention query such that it matches with the features in latent space that then shift its attention to the region it's trying to move its attention to. So it has to, in order to do this, it has to solve internally a world model that is like imagining the next state that it has to attend to. I thought that was very exciting and very fun to see. And I'll show you some results in that in a minute. Yep, so we also tested on ImageNet, classic CV problem. But the question is not how much better can we perform, but what happens if we reason sequentially? What happened was we got this emergence of adaptive compute time, and it's interpretable, at least to a degree. Just as an aside here, I think it's really interesting what happens if you apply the CTM to a low class space, for instance, ImageNet, CFAR10 or CFAR, even CFAR 100, versus a high class space like ImageNet with 1,000 classes. Vastly different behaviors. You get results that you can look at on paper, but this is again an example of understanding the behavior of a model. If I apply the CTM with 20 internal ticks of its recurrence to a CFAR10 problem, what it does is it just essentially assigns a class to 2 ticks. So first 2 ticks is cat, second 2 ticks is dog, third ticks, etc. And all it needs to do in order to solve that task is just bump the certainty up for cat if it's cat, and it basically encodes which class it is just sequentially in time. And it's very difficult to stop it doing that because that is a very, very attractive local optima. For ImageNet, though, you can't do that. You have 20 ticks or 50 ticks. You've got 1,000 classes. You can't ascribe a single class to a single tick. So you end up switching to a different mode of learning where you get all sorts of interesting behaviors, and easy things come first and difficult things come later. And this brings up something else that's part of my research methodology that I like to talk to people about. I call this the problem of minimum sufficient complexity. If you want to solve a problem, you need to decide for yourself where your minimum sufficient complexity is. A lot of the time we like to start with toy problems, and as do I, but often they can send you down a path that doesn't get back to the real thing you're trying to solve. This is an example where testing this on CFAR10 has vastly different behavior and different outcomes than what you would get if you tested this on ImageNet, or that we do get. And I think it's interesting because it's a difficult question to answer. What is the minimum sufficient complexity for this task? And I'd steer away from toy problems. I actually start with much more difficult problems like ImageNet or video learning, and then I dial back when I've understood what's going on. Then I dial back to the toy problems in order to break down the behavior. And I think that that's maybe a bit backwards, but I'd like to pitch that as a different way of approaching this that's worth thinking about. All right, we also tested on the parity task, which is bit flipping. Get a 0, get another 0, your output is currently a 1, and this is a sequence of bits where you have to essentially encode an output sequence. And it's commonly tested for adaptive compute time algorithms in order to see what sort of behavior emerges. We also tested on question and answering on MNIST, which is to say simple modulo maths on MNIST in order to test memory and recall and robustness for out of distribution setups. We did use CIFAR 10 and CIFAR 100 to understand. In a very constrained sense, I had to really push the model to do this, but like to stop it from cheating in the way that I described earlier. But seeing how it tracks the difficulty of a problem versus humans, because there's actually data for difficulty on CIFAR 10 that we can compare models to. It's very cool data. One thing we also tested it on was sort. And what we saw in this was that there was a process where the model would spend time sorting the numbers internally before then deciding when to output the numbers in order, which was quite fun to see. It's another setup where testing how time matters for problem solving and for compute. We can break it down with these sort of toy problems. We also saw the geometry of the problem reflected in the compute time. For instance, if there was a big gap between two numbers versus a small gap in the sorted list, the CTM would take longer to make sure that there were no numbers that would fill that gap. We also tested some proof of concept work in reinforcement learning. This was Kieran, the second author on the paper. He spent a good amount of time on the reinforcement learning and several of these tasks, really breaking down how the model functions in these senses. All right, I want to talk a bit about ImageNet. Images, we use a backbone, like a ResNet backbone. I think we tested all sorts of them, also all sorts of backbones, and we typically didn't get the same performance for the backbones as what we would like for a backbone. Actually, since releasing the CTM version 1, I managed to get the performance up to the same level as these backbones by actually just using a more modern training methodology, like what PyTorch releases. They've got this great documents on how to train ResNets. Works with and without positional embedding. It's almost impossible to tell what the difference is. We trained it on 50 internal ticks, and at each tick in the recurrence, the model predicts 1,000 classes, and it accumulates those. So the actual outputs are t, where t is 50, by 1,000. And what do we do with that? So it's cross entropy on the target class for each and every tick. Now here's the bit of magic sauce here. You don't average that, and you don't take the last tick. In order to actually get this to do behaviorally relevant things, you select the most certain tick by way of highest probability, or what we did was just work out the normalized entropy, and you take the minimum loss. If you just take the minimum loss, it doesn't work, and if you just take the most certain tick, it sort of works, but it breaks down in smaller class problems with smaller number of classes. So basically, you take the most certain and the minimum tick, and you take the average loss. So you'll get 2 ticks. As training goes, they actually converge to the same space, roughly, and gives you decent gradients, and it does know. All right, I'm going. Yep.
Why do you think that works? Why those 2 ticks?
All right, so I spent a long time exploring this. I think I spent like a month on different loss functions here because I was getting really frustrated. I built all my visualization tools in order to understand how this behavior is going, and it's vastly different. I think the reason this works is because the most certain tick is that which the model thinks is certain, and the minimum tick is what we think is certain. So it brings these things together. And I tried a number of things, and I've actually deviated from this when continuing to work on this, and I've come back to it because it actually just works so well. It works better than the other loss functions that I was able to define. But basically, it gives the model freedom to do other things in between the ticks. If you were to just take the average, then you would get this circumstance where the model would always kind of be doing the same thing. And if you take the last tick, for instance, it will be doing all sorts of nonsense, and then right at the end, it just gets to the right class. And both of those behaviors are undesirable for me. It's actually very obvious when you test this on the language modeling task I said, which is kind of similar to a maze task, but with language being very ambiguous and a different path down a very high dimensional maze. You test this on that task, and if you apply this loss, what you get is you get various different predictions of, because language is ambiguous. You know, the cat sat, and you might at some points in their thinking, you get on the mat, which is great. At another point near the fire, relevant. I don't want to penalize it for this. I don't want to push on the fire towards on the mat. Sorry, near the fire towards on the mat. So this lets the model sort of explore the space while only very, very, very carefully pulling it towards the correct answer slightly more. So in ambiguous settings, obviously for ImageNet, it's not ambiguous, well, slightly, but in ambiguous settings, this rarely matters because you don't want to penalize a model for having a kind of like freedom of thought, if you want to think about it like that, but only at 2 points where those things must agree. And this just lets the model be a lot more free to build this adaptive compute timeout. So it lets it attribute earlier ticks to, easier problems. And I'll show you some demonstrations.
I guess the question I have, something you mentioned in the interview you did with Hyun and MLST was the calibration, right? Do you think that I guess it's hard to disentangle everything, especially since the way the task evolve, the inference evolves over time. It's not exactly apples to apples to other neural networks, which might not have the best calibration by default. But could you explain a little bit more about how you quantified the calibration and how that shook out for you?
Sure. Actually, what you can see, if I'm correct, you can see the blog post demonstration with ImageNet stuff, right?
Yeah, yeah.
Okay, cool. So, I mean, this is a calibration here, 5B, this image. This is interesting. So what we did was we said, okay, if we take the class that it's correct with, or the class that it predicts, and we take the average probability over that thought process, not just at the certain ticks. If you take at the ticks that I'm describing, like the most certain tick, during inference, you select with only the certain tick. You don't select with the minimum loss because you can't do that, right? So you take only the most certain tick, and that is the class. And in order to compute the calibration, what we do is you say, what is the average probability over the 50 ticks that you got to think for the class that you just guessed? And then that's what shows really strong calibration.
Okay, yeah. So it really, really isn't apples to apples.
Yes, it really isn't. No. But I don't really care. Like we're trying something new and just having fun with it. So yes, this is why if you're considering just the most certain tick, obviously the calibration is going to be off in the same way that you would expect most models to be. But if you're trying to understand, like, if it's certain very early on, then it would be, on this side where the probability is close to 1 on average. So it is still relevant, but yeah.
Okay, thank you. That's perfect.
I also would have a short question for the loss.
Please do.
If that's okay.
Go
I
ahead.
hope I hope repeat the question because I sent an email recently for this. But I tried the CTM with a stochastically chosen tick, and I was wondering if this is also a loss you went into, because I was thinking to tell the model it doesn't know how many ticks it has, so it tries to get out the best performance out of each tick. That was my hope it would do. And it seemed to work very well with the Cypher 10, but I didn't try it with bigger data sets. So I was wondering if you tried in that direction.
That's a very good question. I think what that's trying to solve is the right problem. I think one thing that annoys me about the CTM is that actually past the ticks that it was trained on, it doesn't generalize that well, which is annoying. You can see it's beginning to try, but the more you train it, the less so. Which is annoying. So I think you're onto something there, but in expectation, how is that all that different from just taking the average? You're basically taking a sparse average.
It does. It's like an expectation value of like a exponentially decaying average of like the ticks. So it didn't work that well. So I was wondering if you have maybe some inspirational ideas that to go in another way of a loss function.
Look, the way that I'd like to do this in the future, and what I'm working on is training the CTM on videos. And I think that it looks very different what you need to do in that space. And in a video space, you would start with fewer ticks, and then slowly over time, you would give it more and more and more and more ticks, eventually to the point where you've removed this start state altogether, where you have the pre-activations, have this learnable embedding that I discussed earlier. Eventually, you would roll that out and you just do streaming training. That's what we're exploring at the moment. Yeah, it's a bit of an open question as to how to get that to work. However, definitely with the structure that we've got for the version 2 of the CTM, we're getting very different behavior when it comes to like what it does at tick 1 versus what it does at tick 20. These things, instead of being algorithmic, they're more data defined, which is what you're after with what you're doing.
I guess this is very interesting also for Hardy because it goes into the direction of like a time series, and you expect that for a long time series you have like an echo state property that the initial conditions are unrelevant for like the attractor which you go to if you hope like you go long enough with the ticks. But the question is how many ticks you need, right? This to happen.
Yeah, it's a very good question. Yep, go ahead.
No, that's it. Thank you.
There was something I tried a while back where I had an output for a sigmoid that weighed like certain time steps according to just like a decaying value. We just start with 1, decrease by like multiplied by the sigmoid output, so on and so forth. That's nice to parallelize, and I could get a smooth weighting over like the number of ticks to run for,
Interesting. Yeah, I'd have to spend some more time thinking about that. I love where we're going with this. It's a difficult question. How do you choose where to stop thinking? And I think not enough people are thinking about this. And I'm glad that maybe this research like brings up more questions and it is able to answer at this stage. It's more exciting to me. All right, I'm just going to discuss some of the results real quick because I do want to save some time. Yeah, so what are we seeing? All right, we have the ImageNet image. All right, this is what the model gets to observe. At all time during its internal tick process, it can then construct queries via synchronization that then have keys and values that come from a ResNet backbone. Where those queries fire closely with the keys are visualized with these attention maps. We've got 16 heads. This is what you see at the bottom, and this is just the average in the top left. This is the classes being predicted and the certainty over time. When the certainty is red, it's incorrect, and when it's green, it's correct. In this case, the model is very certain quite early on. I'll show you an uncertain example in a minute. But as I run this forward, you can see how the attention is not static by any means. This is what we discuss as being the gazing behavior of the CTM in the paper. The arrows that you see in each of these images, I basically computed those by not really taking the argmax. It's like a center of mass with islands. I had to choose one, otherwise building this algorithm kind of breaks. Again, this is about how do you build your tools. And interestingly, you can see there's a lot of salience and regions where the model focuses on salience here. And this was really nice, seeing some sort of observable actions. Really interestingly, in the beginning of learning, it doesn't look around at all. This only comes with, several, maybe 50,000 steps of training. Then you see more and more looking around, and it gets more and more diverse and more rich. That was really gratifying to see. All right, let's see if I can load up another example. Here's a good one. I don't think it gets this correct, but it is interesting to see how the certainty increases. Right. So doesn't get it correct, but you can see how the certainty for whatever it's guessing goes up over time. And the sort of behavior is what we typically see. Maybe one more example. Yeah, they're all dogs. Well, ImageNet is just dogs. So so feel free to go explore this website and have a look for yourself. I like to show this website as I like visual things. So this is essentially what we do to build this UMAP. So one of the members on our team, Jeffrey, he has a neuroscience and maths background. And when we were discussing this idea, he said, yeah, apply UMAP to the neurons to see what's going on, because this is something that has been done for brain signals in order to see things like what do they call them, traveling waves. So what we were after is, can we see traveling waves? And maybe not, maybe so. But the point is, it's really, really interesting to see how the neurons fire over time when it looks at an ImageNet image. If you spend time looking at this, you can see different islands of activity where you can actually see the, let me open this large so that it makes more sense. Yeah, all right, so especially in this top right corner, you can see that there's sort of movement of the activity down. And the way that we compute this is we take many, 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 many examples and the neurons over a long time period and build like a big feature matrix. And with that feature matrix, we collapse it with UMAP into 2 dimensions. And the reason we take many different images is to make sure that it's not biased towards a single image. If you take just a single image or a handful of them, it's very obvious that you get these like traveling wave effects, but that's spurious. Yeah, I want to talk a bit about the mazes now. So on this website, we have this fun little tool to actually see how the model is behaving. And I think it's worth pointing out, why did I do this? To be honest with you, I just wanted people to like interact with the website. I wanted people to find this enjoyable. So I spent some time figuring out how to turn a small version of the maze model that we trained into something that can run in a browser. So this model is running in the browser. What is the task? As I described with a maze, it's moving from the red pixel to the green pixel. And these are the 8 attention heads that it has. This is worth pointing out that in this case, it's pretty obvious that 3 of these attention heads have a broad perspective and the others have a narrow perspective. This will change as it's thinking about the task, but I'm going to hit run, and then you'll see there will be an attention overlay that is the bright spot that you'll see moving around, and you'll see a path. It'll be a rainbow looking path, and that is the path at that internal tick that the CTM is currently predicting. So I'll hit run. And I'm going to run at a slower FPS so that you guys can see a bit better. All right. The bright spot that's moving forward, that is where the CTM's query on average is firing the most. Okay, it's just the average of these attention heads at the bottom. And this path that it's currently predicting is the path at that tick. And I think pretty fun. In this particular web demo, we can teleport and we can auto-solve. Yeah, we can run this and it breaks down sometimes, but then sometimes it gets there. And we can see how, particularly with the small model, not the big one, the small model, at these weird intersections here, CTM's terrible at this. So it solves it perfectly if it's there. And this is because it's a ResNet backbone. Small ResNet backbone, and this convolutions are killing things. As you can see, it fails there, but it succeeds convolution artifacts. Yeah, so something that's important about go back to my slides. Something that's important about the mazes. Yeah, I think I just described all of this, but there's this weight token or this weight class. It's basically because when you're training it, you set your maximum path to 100 or 200, but the path might be 10. So you use weight as like a padding for this. This case, it's a single optimal path. There's no ambiguity here. And we use 75 ticks during training for the maze tasks. Yep. Importantly, it's the same loss as the images, the 2-tick thing, but there's this concept of an auto curriculum. And what is this? If, for instance, the CTM is predicting 5 steps forward, if the CTM is predicting 5 steps forward correctly, we supervise it for 6 or 8 steps forward. Then as the learning progresses, it gets better and better and iteratively better at solving the task. We were fair and we trained the comparator methods like the RNNs and LSTMs in the exact same way, but after a certain number of ticks, they just break down. And I think it's got to do with a combination of the type of representation being this fixed representation, the snapshot one, and also the gradient problem that we know with RNNs. Interestingly, you can see when you watch the RNNs and LSTMs reason about this, they they get themselves stuck in a loop. They sort of reason a bit and then they come back and they get stuck in this. And I think it's, again, because when you interpret this output, you have to then squeeze all of this information into like a small snapshot vector versus the CTM that can use the entire time scale or all of the time to basically craft that solution into something that is much richer. Yeah. All right. So I want to discuss some of the principles of the CTM again. I'll probably fly over this because I want to discuss some more things. But many realistic problems in this world are time-based. They are sequential. And natural intelligence is, without a shadow of a doubt, temporally bound. And I want to ask the question with my research is, how different will the AI of the future be if we pay attention to this feature of reality? Representation in brains are more than just a snapshot. And I think I've spoken enough about that. We originally called the CTM the asynchronous thought machine. But because then we had synchronization as a feature, and this, it became very confusing for even us to talk about. We renamed it, I think, 2 weeks before we released it. I liked calling it the asynchronous thought machine because the point I was trying to drive home is that data can be static. In everything we showed in the CTM version 1, the data is just static. It's about the process that you apply to it that's dynamic. And I wanted that to feature more strongly, but I think it featured enough. All right.
Look, maybe I want to push back a little bit on this because I
Go
think
ahead.
that, the fact that you have this global tick shared across the network, that certainly gives me a sense of synchronous processing rather than each layer or neurons having their own internal tick. So in that sense, maybe I guess continuous thought machine is more appropriate.
Oh yeah, I totally agree with you.
Yeah.
By asynchronous in this case, I mean just that the data is not a sequence. It's just like a static image, for instance. Yeah, that's all I meant.
Oh, I see. Okay, so you don't mean it in the
Yeah.
same sense that I okay.
No. I don't. Although interestingly, I have tried a very weird experiment to actually make that work, Heidi, and it's fascinating, but difficult to get it to work and train it nicely. All right, so the last thing I want to drive home is that light biological inspiration tends to result in novel behaviors, which is great. I also mentioned earlier that some of the engineering problems that we overcame with solutions, the fact that they look like biology in maybe an oblique sense, if you look at them sideways, like synchronization, it's great. That speaks to me a bit, and that makes me feel as though, there's more shared about intelligence, about what it is, than what we often think about. And let me see if I can unpack that a bit. What I mean is that if you get a machine system to implement what looks like intelligent behavior, whether it is or isn't is an open question, but what looks like intelligent behavior, and you see what it is that you built in order to make this happen, and then that looks like something that brains do, I think that that's really cool. I like that a lot. All right.
Luke, I have a question. How do you like draw the bar between pulling ideas from biology, but then also like remembering about like the constraints of biology due to like evolution, right? So like to get
it's a very, very good question. I know where you're going with this, Manish. The prime working example for me is spiking neural networks. I think that they're really, really fascinating and worth exploring. I don't want to explore them because A, they're difficult to work with, and B, I have my very, very opinionated opinion here is that there are things that nature has implemented, that evolution has implemented, that are a consequence of hardware constraints. And I think that spiking can fall into that category, not necessarily. The open question with spiking neural networks, from my point of view, is do we get our intelligence as a consequence of the hardware constraint, or is that just a hardware constraint? And for this particular example, in spiking neural networks, the spikes are spikes because they have to travel over such a massive distance in the brain. And this needs it to be an impulse in order for the signal to noise ratio to be sufficiently high. So this is what I like to ask is the good example is the neural network models. Yes, they're not like brains, but maybe they're a good enough function approximator that we can get something out of them.
Yeah, because this brings me to like, like for example, Hebbian learning, like fire, like together, neurons that fire together, wire together, whatever. So like, like limitations of biology, like when humans are born, like the size of like the head is obviously limited. And so due to that, like maybe it was optimized for like heavily weighing on the temporal aspect. So does that bring you any thoughts regarding this or?
Yeah, I think it's a great way of thinking about research and what you want to build. Uh, for me, I haven't given it enough time to give you haven't given it enough time of my thinking to give you a concrete, real opinion on this. However, I think what's more important is understanding or trying to think about what intelligence implements, the behaviors and algorithms that intelligence implements, and trying to mimic them, and then drawing the parallels. I think that for me is a more uh, tenable way of doing active research in the space. Yeah, I hope that helps. I wish I gave you a more concrete answer, but it's difficult. Yeah. All right. I'm going to talk a bit about what in our like NeurIP submission to this paper, we right at the bottom, like last appendix, we spoke about emergent phenomenon, and it's interesting. So I'm just going to fly over a few of these. Uh, the periodic nature of the neural dynamics emerges over time. They're usually much more flat in the beginning of training. So it's interesting that learning causes periodic neurons. I'll show you an example of this. No, not this one, but about a quarter of the way through learning, when you're observing this with your visualization tactic that you have, I notice that the CTM will go down one route in a maze and then figure out, oh, it's not that one. It'll come back and then try again. This was fun to see. I showed you earlier, there's broad versus narrow attention heads. And this is the next one I really want to show you is under heavy constraints. So if your path length is like 200 and you only have like 30 or 40 ticks to solve the problem in, the type of solutions look alien. So the ones that we showed you with the nice tracing out of the path, that looks really human and identifiable. But the one that I'm going to show you next, much more alien. And I think that that's really fun. So this is it. All right. So why do I say this is alien? All right. That's what the solution looks like. On the right is essentially where the CTM is attending. Instead of following the path like it would usually, which is what we saw with unrestricted versions, we would see that the CTM then jumps forward, traces back, jumps forward, traces back, jumps forward, traces back, and only right at the end, if I rewind there, the path's completely wrong. But I'd take 2 more steps and right at the end, it outputs the correct path. So I'll play this again and just watch the image on the right. That's a very weird way of solving a maze. And this is fun because you see these weird emergent behaviors pop out of the system when you actually constrain it in different ways. Does this mean anything besides it's kind of interesting? Not really, but you do see these things happen when you have the tools to unpack them. I think that's what I'm trying to drive home today. Alrighty. Any questions at this stage before I show you some hints at version 2 of the CTM?
I would have 2 questions for you. One for the maze you just showed. I thought, is this maybe like just an artifact of how the loss is defined? Because getting like the right ticks at the end is maybe something that's easy because it's close to the goal, and that's why it's trained to go in this direction with a few ticks. Do you think this could be the reason for this?
Yeah, potentially. It's probably a compounding effect of multiple things, but I can imagine that features, yeah.
Okay, and my second question is about bottleneck. Like I tried to implement the CTM with a Cypher 10 and tried because I like this idea of this internal refinement tick that essentially queries in your question to the static data. So asking like new question like, I don't know, let's look on the top left and then look on the top right. And then if I see this, I change like where I look on the picture. So I would hope or expect that with this idea that with the more ticks you give, the just better it gets. But it seems to have a bottleneck at some place. And I was wondering what the bottleneck could be. I was thinking maybe the feature extractor from like the values and keys could be the reason. Do you have like any insight where you think the bottleneck could be for this system?
I think the way that we build visual systems with convolutions, maybe the idea of the static images of the same resolution that we give to a model and expect it to be static about it is even the CTM with the query that's very half a small step towards where I want to go with it. And I'll show you some more in a minute as to what I think how we should be building visual systems, and it'll make more sense.
Oh, okay. Thank you.
Yeah. Okay.
I guess I have actually no, I'll save it for later.
Yeah, maybe I can just show you guys some more stuff, and then we can. I'm not sure about how the question Q&A works, if it's during our time or if we go over time, Heidi, because I see we've only got about 12 minutes left.
Yeah, so I mean, we have the room over here, so that's not a problem. In the sense of like, there's no hard constraints. But you know, if you have to run after, let's say, our official.
I don't. I'd be happy to stay on and talk and answer questions more after this.
Yeah, for sure. I mean, I don't have any hard constraints after this, so maybe we should make sure to finish the presentation part. And there's this final Q&A where we stop recording and just, discuss ideas after that.
Got it. All right, let's leave questions for then at that stage then. All right. Okay, so this is a bit of a sneak peek at what I'm currently working on. I'm going to explain what, but I'm not going to explain how, because I've got to keep some secrets for us to release later. But basically, I've been exploring this idea of Activision and the power of choice. Just a few days ago, 2 colleagues sent me this essay by Vincent Sitzman on the flavor of the bitter lesson for computer vision. And I highly recommend looking this up. It's a very good read. It captures a lot of the thoughts that I want to express to you, Felix, but please read this. It's brilliant. Basically, as a summary, current vision tasks are static. And the task is an intermediate representation. Classes, segmentation masks, 3 representations, etc. But intelligent action is actually the North Star of visual understanding. If I ask you, what defines a human as being intelligent? You don't say that they know if it's a cat or a dog. You say that they are allergic to cats, so they own a dog. So it's this action based on understanding. And intelligent actions are strongly well-defined. And I think that understanding a visual system should be by way of its action, not by way of, can it give me a segmentation mask? I think foveated views require intelligent decision-making. What are foveated views? Eyes, all biological eyes implement foveation, which is to say, when you're focused, you can see very clearly where you are, but all of this peripheral vision is blurry. It's low resolution, if you wish. And that means that I have to choose where I'm going to put my eyes. If I want to understand the world that I'm in, I have to make an active decision about putting my eyes here or putting my eyes there. And this is as a biological constraint. We spoke about this a minute ago, Manish, this idea of what parts of biology and what parts of reality should we try to encode in our models. For me, foveation and the consequences of foveation, more importantly, so the ability or necessity to choose, is what I think is important. There's a brilliant book called What is Intelligence by one of my favorite researchers, Blaise, and it's brilliant inspiration. And one of the take-home messages here is that nature implements intelligence all the way down. So that is to say, cells are intelligent, eyes are intelligent, brains are intelligent, humans are intelligent, etc. And this is a strong way that I'm building out the CTM version 2. Won't go into too much detail as to why, but intelligence in a more distributed intelligence, a gentle fashion is kind of fun. All right, what is the cost of passivity? So static images, basically, in the visual sense. It's not biologically plausible, doesn't use this decision-making process. It's a massively high cost associated with it. If you want to understand a visual scene with a CNN or a VIT type model, it has to process that whole scene simultaneously and at full fidelity. It's hugely wasteful, first of all. That's fine. That's something we can measure. But it also forces unnecessary detail into its representation. There's this commonly known thing for CNNs, and it's true for VITs too, that texture often is the defining feature of how the models decipher which class they're in. There's a great paper from 7 or 8 years ago, exploring how CNNs will learn texture, not shapes. And it's the texture bias, I think it's called now. And I think that this is a consequence of static passive models. I think that the central challenge of perception is choice. The problem is choice. Where to look, at what scale, and in what order. An active model must solve this problem in every moment. And if it does that, it gains access to a powerful learning signal. So this is, we went here a bit with CTM version 1. It has to look around. I don't think we pushed it enough. And I think that an active model that must solve this problem in every single moment accesses something powerful, which is that learning signal of what to do next. And I'm going to show you some examples now. Some examples, maybe one example, I'm not sure. All right. So, where am I at? Yeah. Can you guys still see my screen? Some HTML thing?
Yes.
Yep.
Yep. All right. So finally, Hadi, now we're getting to what I was talking about earlier. This is the example of how I conduct experiments. And I'd love to share this with you guys. All of this code that builds this HTML is vibe coded entirely because it's HTML and JavaScript and CSS, easy. And fun fact, you can push this into weights and biases. I don't know if you know this, but you can literally drop HTML into weights and biases, just log it and it pops up in weights and biases. And you can interact with it. It blows my mind. I think that's so much fun. Yeah, literally these files I've just loaded from weights and biases. And you can actually interact with them real time. So what are we seeing? Alrighty. Blocks. What are the blocks? This block, for instance, is a small foveated view. There's its foveation ring. So this is very low resolution, and this is a high resolution set. It's like an eye, The job of the model is to classify what this image is. And it's got internal ticks to do so, and it must move its perspectives around and gather information in order to do so. And this is what it looks like. So you can see how all the blocks are changing. I'll pause it right towards the end. Interestingly, you can see the background blocks over here. They're all texture-based, of course, because the background is texture. And this is what we see with neural networks. The blocks that actually are ascribed to the face, big blocks that are shape biased. For instance, if we look at this, what is it seeing? This is what the model is currently seeing. Well, sorry, this particular block that the CTM is moving around is seeing it's an eye. And if I play that and I actually look at the perspective of this particular block, you can see how it's focused on the eye. And this sort of behavioral driven stuff is what I'm after. Look at this one, it's focusing on the mouth, and it's basically building out these features. And as you play this over time, same model, all right, but a different class, you can see how the blocks focus in totally different regions. The snake's head, this one's great. So in this case, the CTM can control, in all these cases, the CTM can control where the blocks are, what their aspect ratio is, how zoomed in they are, and what rotation they have. And in this particular instance, you'll notice that the aspect ratio and zoom corresponds with the image. As I play this forward, you can see how these particular blocks end up with a squashed aspect ratio because look, they're looking at something that's a squashed aspect ratio. And
wait, so how does this
you know,
work? Each of these blocks, okay, we interpret each of these blocks as a foveation block, and what are the free parameters that determine their shape and location? So I imagine there's like an X and Y position, and then width
X, Y, zoom, aspect ratio, and rotation.
and these are free parameters that you learn, or how does
Are they? Oh,
yeah, I'm basically curious, are you learning these, or are they sort of inferred as ticks go on?
I think that
Um,
they're output by the attention query.
yeah, something like that.
Oh, so you're kind of decoding something from the synchronization matrix.
Yeah, something like that.
Okay. I see. Okay.
Yeah. But well, I wanted to unpack some more of like how the system works, like what I'm building here, right? In terms of visualization, because that's what I want to talk about.
I see. Yeah.
Is right. So we've got this, but I decided how do I get more from this? And then you can do things like looking at the trails of where these things are going, or you can look at the paths that they trace out over time. So we can change the different settings and look at the paths and how the blocks move around and all sorts of things. And then on the right-hand side here, we've got attention. And you can see if you accumulate the attention where it's actually going. All sorts of fun things like this. Let's see something else. And also as the model's thinking, you can see how its classes change over time. Here's some real-time UMAP stuff. This is really fun. So we can choose, for instance, let's normalize the neuron colors by a neuron by neuron basis. You can change the minimum and maximum size of things and play this forward. And you can get all sorts of different perspectives on what your model's doing by playing with these things. So if we make this really small and we drive down the alpha, we can actually then start to see the traveling waves that emerge. And just this process of digging down into your model on this sort of level is something that I think is quite valuable, and you can, for instance, unpack the different layers. So this is there's 3 attention or 3 CTM layers here, and you can see what they're doing in different perspectives. It's good fun. All sorts of things like implemented gates and predictions and have nested things going on here. But the point I want to make with this is just you can just go wild. And just like LLMs are getting better and better and better and better, your unpacking of your experiments can just bootstrap on itself. Every couple of weeks I go in and rethink this and I think, okay, what can I add? How can I change? Last night I changed settings. So there's certain ways I come into these things and I resize this. Yeah. Now it sticks. So it gets saved in the browser, and then next time I load it up, it's there. It doesn't go away. And you can change the frames per second, and you can see how it's going to look at really slow motion. And I think this is valuable. I've unpacked many different aspects of this problem via doing this, and I think it's worth being a good take-home message today. Yeah.
Yeah. As long as you can, the difference is if you can imagine it now, you can probably do it in a very short time. Crazy part.
Precisely. Yeah. Like I said, the problem of being a researcher now is knowing how to apply your intelligence.
Mm-hmm.
You can't do things the way that they used to be done.
Mm-hmm.
It's not going to work. All right. So I think I'm going to stop sharing my screen and we can have a. There we go.
Okay.
Cool. I think that's my full presentation. Thanks, everybody.
Yeah, thanks for joining us, Luke. This is amazing. Let's thanks the presenter, and I'm gonna stop sharing now.